For decades, enterprise computing was constrained by a strict one-to-one relationship, one physical machine running exactly one operating system. If an application required 10% of a server's processing capacity, the remaining 90% sat idle, wasting electricity and rack space. Virtualization solves this hardware bottleneck by introducing an abstraction layer. It creates an isolated, logical version of computing resources, like CPU, memory, and storage, so that multiple operating systems can operate on a single physical machine without interfering with one another. This 3D schematic illustrates the core architecture. At the base is the host, the physical server providing the actual hardware resources. Directly above it sits the virtual machine monitor, or hypervisor. This specialized software acts as the critical intermediary between the physical components and the operating systems running above it. By intercepting system calls, the hypervisor allows this single host to securely multiplex into multiple distinct guest operating systems. To the guests, it appears they are running on dedicated, bare metal hardware, but they are actually sharing a single pool of physical resources. A correctly deployed virtualized environment provides 4 specific characteristics. First, isolation. A failure in one guest does not crash the host. Second, sharing. Multiple guests divide the same physical CPU and RAM. Third, emulation. A guest can run legacy software independent of the modern host hardware. And fourth, portability. Entire logical servers can be moved between physical racks instantly. Inserting this layer of code between the OS and hardware severs the dependency on physical infrastructure. Scaling a data center becomes an exercise in software provisioning rather than physical hardware installation. Because multiple virtual machines are competing for the exact same physical resources, the hypervisor must act as the ultimate gatekeeper, scheduling every cycle of CPU time and allocating every block of memory. This split-screen architectural diagram shows the 2 primary classifications of hypervisors. On the left, we see a Type 1, or native hypervisor. Notice that it installs directly onto the bare metal hardware. There is no underlying operating system, which provides maximum performance and security. On the right is a Type 2, or hosted hypervisor. Here, the hypervisor runs as an application on top of an existing host operating system. It relies entirely on that host OS to manage hardware access. Trace a hardware request through both stacks. On the left, the packet hits the Type 1 hypervisor and executes immediately on the hardware. On the right, the Type 2 request hits the hypervisor, is translated for the host OS, and only then reaches the hardware. That extra step introduces a permanent latency penalty. For exam purposes, you must categorize these correctly. VMware ESXi and Microsoft Hyper-V are Type 1 architectures. VirtualBox and VMware Workstation are Type 2. The presence of a host OS dictates the use case. Type 2 is restricted to local testing and development, while Type 1's direct hardware access makes it the mandatory architecture for running enterprise-grade cloud environments. Inside a Type 1 architecture, engineers face a core compromise. Do you pay the heavy computational cost of completely emulating physical hardware, or do you physically modify the guest operating system so it knows it is virtualized? In this flow diagram of full virtualization, the guest OS is completely unmodified. It believes it is interacting with a real processor. To prevent system crashes, the hypervisor must catch every single privileged instruction and dynamically translate it into a safe hardware signal. The advantage is perfect compatibility. Any operating system will run. The disadvantage is high processing overhead. Translating instructions in real time acts as a constant tax on the CPU. Now look at the shift to para-virtualization. Here, the guest OS kernel is explicitly modified. Instead of sending standard hardware commands that need translation, it bypasses emulation and issues direct hypercalls straight to the hypervisor. There is also partial virtualization, an older approach where only select hardware components are virtualized, but this is largely a legacy implementation compared to full and para-virtualization. The choice between full and para-virtualization often comes down to source code access. In open source environments like Linux, engineers modify the kernel to use para-virtualization for maximum speed. For proprietary systems like Windows, where the kernel is locked, administrators must rely on the emulation of full virtualization. To prove a functional understanding of these concepts, you must be able to map out specific platform architectures. We begin with Zen, the open-source pioneer of para-virtualization. Look closely at this Zen blueprint. The foundation is the physical hardware, and sitting directly on top of it is the Zen hypervisor. It has an incredibly small footprint, handling only memory management and CPU scheduling. Above the hypervisor, Zen isolates processes into domains. Domain 0, or DOM0, is the privileged management node containing the actual hardware drivers. Domain U represents the unprivileged guest virtual machines running the modified operating systems. Execution flows directly. Because the DOM-U operating systems are modified, they communicate with the hypervisor strictly through hypercalls, achieving near-native hardware speeds without emulation. Compare that to this VMware blueprint, illustrating full virtualization. The virtual machine monitor sits above the hardware. The guest OS blocks on top are unmodified. When a guest attempts a privileged operation, the VMM traps it and translates it dynamically inside that middle layer. Being able to draw these two diagrams demonstrates that you understand the mechanical difference between modifying a kernel to send hypercalls and using a VMM to trap and translate unmodified instructions. Microsoft Hyper-V uses a partition-based architecture. As seen in this blueprint, the Type 1 hypervisor sits on bare metal. Above it is a primary parent partition running the Windows Management OS alongside isolated child partitions for the guests. The parent partition maintains exclusive control over the hardware devices and virtualization services, routing physical access for the guest operating systems executing inside the child partitions. Until now, we have examined hardware-level virtualization, but the machine reference model proves that abstraction can be applied further up the software stack. This diagram illustrates operating system-level virtualization, commonly called containerization. There is no hypervisor. Instead, a single shared OS kernel allocates resources to multiple isolated user spaces, or containers. It is highly efficient because it eliminates the need to boot separate guest operating systems. Ascend one level further to programming language virtualization. The Java Virtual Machine creates an execution environment where compiled bytecode runs perfectly on any underlying operating system or hardware architecture. Virtualization functions as a universal principle of abstraction, used to sever rigid dependencies at the hardware, OS, and application levels. Take these microarchitectures and deploy them across thousands of servers, and you build the infrastructure of a modern cloud data center. Operating at this scale requires 4 distinct pillars of abstraction: server virtualization to manage compute cycles, storage virtualization to pool hard drives into unified logical arrays, network virtualization to build flexible software-defined switches, and desktop virtualization to host remote user environments centrally. This isometric view visualizes the concept of multi-tenancy. Using strict hypervisor boundaries, cloud providers can place direct competitors, Tenant A and Tenant B, on the exact same physical blade servers, keeping their data logically separated and completely secure. Because these servers are now software files rather than physical boxes, the environment achieves elasticity. When traffic spikes, the resource manager instantly provisions and boots new virtual machines to absorb the load, and destroys them when the surge ends. Without the abstraction of hardware resources, cloud providers would lack the high resource density and millisecond provisioning speeds necessary to sustain their current on-demand economic models. Your final exam requirement is evaluating the operational trade-offs of this technology. This balance sheet breaks down the business realities of a virtualized infrastructure. On the positive side, virtualization drastically reduces capital expenditure through server consolidation. It provides dynamic resource scaling, and it allows for instant disaster recovery by turning entire operating systems into portable snapshots that can be migrated live. On the negative side, there is persistent performance overhead from hypervisor emulation. Consolidating resources creates a dangerous single point of failure where one physical crash takes out multiple VMs. Finally, because spinning up VMs is so easy, administrators often face VM sprawl, wasting storage on unmonitored systems. To navigate these trade-offs, you must know the exact structural layouts of Xen, VMware, and Hyper-V, and be able to clearly articulate the difference between a hardware hypervisor and an OS-level container. Virtualization is the engineering blueprint that physically allows the modern internet to scale. By abstracting the hardware, we turned the limitations of metal and silicon into the flexibility of code.